So our next speaker, Beat Hörmann, joined supercomputing system for his master thesis in deep learning for microscopy imaging for fertility analysis. His work is focused on machine learning for image segmentation and image instance segmentation in life science applications. Beat Hörmann will present an automated cell counting algorithm based on convolutional neural networks he has developed. As you've seen, I don't know what you're going to talk about. I'm very interested to find out. Welcome, Beat.
Thank you very much. Who of you knows what you can see on this image I'm showing you right now? I guess most of you have a pretty good idea of what that is. It's a couple of cells. To be precise, it's a microscopy image of L929 cells. That's a type of cell that is for example, often used to assess the influence of new drugs on cancer growth, for example. And the key point to assess there is usually the cell count over time. And you wouldn't believe it, that's something that's often still done manually, actually. So what I wanted to present is that so much time can be saved just by automating the counting of those cells. But the critical point is we have to make sure it runs in any lab that actually wants to count these cells. With that, I'd like to welcome you to my talk. You can count on us. Preclinical automated cell counting with deep learning on the edge. First, I wanted to present you who is the team who did this work that I'm going to talk about. First and foremost, it's our partner Inome, who has developed a microscopy system called SenCell-OL, and software that goes with it, an analysis and image analysis software. And my company, Supercomputing Systems, especially the team with Pascal Kaiser and Dr. Christoph Bühler, we were in charge of developing the cell counting algorithm. Let's recap the goals that I want to talk about in this talk, and the goals that we had for the project. We want to support labs with artificial intelligence for automated counting of cells. We want to make sure that it runs in any lab regardless of their infrastructure, meaning regardless of their hardware compute power and also regardless of their internet connection. And we wanted to keep the development effort as small as possible for our partner. What was the approach that we took for this project? First, I'm going to talk about the ground truth generation. Then I'm going to talk about the functional prototype that we set up. That is a prototype that has no hardware limitations and is just there to do the task that we want to do want the final algorithm to complete as well. Then we're going to talk about downscaling the prototype step by step and continuously evaluating how well it is doing. And finally, we have to integrate it in the existing solution that was developed by our partner Inome. Let me first talk about the ground truth. On the left-hand side, you can see the microscopy system that our partner developed. In this microscopy system, you have 24 cameras. And each of these cameras produces an image like you can see on the right-hand side with those L2L cells. Full-size microscopy images, roughly 2,800 by 1,800 pixels, and they cover a wide range of lighting, focus, and cell count conditions. Our ground truth consisted of segmentation maps, as you can see on the right here. These segmentation maps cover 1/4 of the image, roughly, to spare our partner a little bit of the hard work of actually doing the ground truth generation. And from these segmentations, we could also infer the cell counts that we actually want to come up with in the end. We didn't have a large data set, I have to admit. We had 33 training images, 7 validation images, and 7 test images. But we thought this problem is not that hard in terms of machine learning, and we should be able to work with that. Let me show you the functional prototype, our pipeline for that. You have the input image on the left. Then we have the instance segmentation done by UNet architecture. We implemented that in Python and TensorFlow. We had a modified UNet algorithm already around, which is why we chose that. We had a cleanup and instance separation stage where we removed small particles and eroded the image a little bit to make sure no false connections are made between cell segmentations. We finally counted and detected the position of the cells, and we would then come up, for debug purposes at least, with that output, and for the actual algorithm, we would come up with just the cell counts and their positions. Let me talk a little bit about the downsizing. We came up with the following requirements to be able to run in any lab, as I said. We wanted to run on a Windows 7 PC with 4 GB RAM, take a maximum of 5 seconds per image, and reach a 95% accuracy for the cell count. As I said, the downsizing started from our prototype that was a UNet-like CNN with 21 layers, which had up to 1,024 filters, and was roughly 8 GB in size. So the main changes that we actually performed were really a reduction of layers and filters, just downsizing the net very much, and also reducing the number of input channels, which is a similar category, and some small code optimizations where we found out, okay, this part takes very long, we can improve it, let's just do it. What we already used in terms of what can be used for downsizing neural networks was small compute activations, which means rectified linear units instead of sigmoid activations, for example. And what we did not use was a reduction of float precision that we could have done, for example, or binary neural nets. Those would be steps that we would naturally do the next time that we have a similar project, and maybe a little bit more time as well. Among other nets that we worked with here were the CNNX, as I call it here, and the CNNY, both with very low amount of layers and a low amount of filters. Here you can CNNY. You can still see the UNet-like shape, but it's shrink down very much. And so this was actually the net that we came up with in the end, that served our purpose well. Oh, I'm sorry, I skipped. Yeah. Let's have a look at the results that we achieved with this net. On this slide, you can see a chart that shows both timing on the x-axis and the memory consumption on the y-axis. On the left, you can see an inference run for 1 image. On the right, you can see an inference run for 7 images. And as you can't see anything here, really, I'm probably gonna skip to this slide and tell you that for a single image, we have a processing time, an average processing time of around 10 seconds. For 7 image total, 35 seconds, which means the average processing time for 7 images is 5 seconds and meets our original requirement. Also, for the maximum memory consumption, we're well below the threshold that we set ourselves for this project. Let's have a look at the results of the segmentation. On the right-hand side, you can see an example output, also with the cells that we detected marked in with a yellow dot. Well, we had 3 pixel classes in the end for our classification. The F1 scores for the normal cells in the background are fine. For the detached cells, which are shown as blue dots on the image, and that are simply cells that are not detached to the bottom of that assay anymore, the F1 score is not that good, but our cell count results showed that it doesn't matter that much, actually. Which leads me to the cell count, which is actually the number that we wanted to predict in the first place. And here you can see an overview. We have small deltas in number of total cells that we counted differently compared to our algorithm, with an average delta of 5 or roughly 6%, let's say. We didn't quite meet our requirement, but for our purposes, it was close enough. And we kind of reached a Pareto front there, so we had to decide on whether to get faster or more accurate. Then finally, the fourth and last step was the integration in the software of our partner Inome, which was simply building a file-based API and a Python executable. And here you can see an example user interface of the software of our partner that shows the development of the cell count in one of the assays over time. What did we learn in this project? As in any artificial intelligence project, really, or any deep learning project, it's challenging to cover the input image variability. In the end, we managed fine, but at the start, we had some issues there to finally get to know all the different conditions that the image could be taken in. Our gut feeling regarding the complexity is reliable, as seasoned, let's say, deep learning engineers. We can really know what is feasible and what is not. We reached a Pareto front, so we needed to decide on how to prioritize between timing and accuracy. In the end, we reduced the filters, mostly to achieve speed and not to save memory anymore, which we didn't necessarily expect at the beginning. And as I showed you, there are many more methods available, even without hardware choices like, I don't know, some compute stick for a lab. With that, I'd like to conclude. We implemented an automated and reproducible cell counting algorithm for any lab. We evaluated our solution successfully on our test set. We did all that within 30 person days and 3 weeks total. And finally, I can say we did not conquer the world yet with our algorithm, but it's a start to alleviate a lot of lab workers from their pain of counting cells. Thank you very much.
Thank you, Beat. And how was that, presenting without an audience?
Yeah, it was strange, but nice.
Okay, very good.
Still nice.
We got a question that just came in. What is the advantage of solving this task with segmentation instead of a regression?
I mean, sure, you can probably save some in terms of net size for when you use regression, but we thought that it would be beneficial to have a debug output in the middle of our algorithm, so we can really kind of better understand our algorithm and more be able to tune it more to our needs, actually. Mm-hmm. So we didn't choose an end-to-end pipeline, so to speak, yet.
And why is it important that the algorithm can be executed on low-performance hardware? Is health not important enough to buy expensive hardware?
It seems so. I mean, according to our partner, a lot of labs still run on very, very old computing hardware. And I mean, if you want to upload images to the cloud, you need a pretty good internet connection. And if you do that, I don't know, every 5 seconds, it's probably not a good idea. But yeah, maybe we should spend more on health, yeah.
How many parameters are involved in your algorithm?
I'd actually have to look it up. Maybe I can write it later in the Q&A again.
Okay.
But I think in the... No, I'm not sure right now, sorry.
All right. Are they highly correlated?
Not to our knowledge, no.
All right. We have another question that just came in. Yeah. Cells on the edge of the image are not counted. Is that an artifact of the processing pipeline or of the ground truth inputs?
Yeah, that was actually a decision that we made to make sure that we don't have artifacts from actual cells that are cut off at the border, because we only wanted to count those cells that are fully on the image, and on the border we would sometimes have actual cells, but that were not big enough to hit our threshold, so we just kind of drew a border in which we counted.
People are very interested in your topic. There's another question that just came in. Did you try some more optimized methods, for example, efficient depth?
Yeah, we would have loved to, but unfortunately, as I said, we had 3 weeks to do this, so we kind of stuck to the basics that we knew would work. And but for the future, for the next generations of the algorithm, I'm pretty sure that this would be a nice way to go as well.
And I'm turning again. What was the resolution of the input data and the final receptive field of the network, or how many max pooling layers have been involved in the UNet?
So one step that I skipped in our pipeline was that we actually have a chessboarding of the input image, and I think our input image in the end was like something like 78 pixels. And that was also our receptive field, as far as I know. Yeah.
And no, I was just told there's one more, but we're running out of time. I'm so sorry. But
yeah,
thank you very much.
I can probably answer it online.
All right. Thank you very much, Beat. Thanks.
Thank you.